べるから英語で質問するから食べさせてという質問がありましたので、食べてもらって構わないということで、後で冷えてるやつ持ってきますので、これは見計らって皆さん後でコップでお茶でも飲みながら、とりあえずまず集中して話を聞いてもらって、でその後雑談タイムになると想像しますので、ぜひとも活発に話をしてください。後で最後に集合説明をします
皆さんこんにちは。今日はですね、ティータイムセミナーですね。ということで、外国人の先生をお呼びしています。ですね、理化学研究所、講師があります理化学研究所で、研究されています、原奈美先生です。で、彼女は、出身は、アルジェリアという国なんですけれども、国籍はフランスということになっているそうです。その辺の事情は多分最初に話してくださると思うので、今日はですね、ご専門はですね、原子核の物理学なんですけれども、そこにありますように原子核を理解することで、宇宙まで理解できるという、広い話をしてくださる予定です。ぜひですね、話の途中でもどんどん手を挙げて、わからないことはどんどん聞いてください。じゃあ始めます。よろしいですか。
こんにちは。My name is Sarah NAIMI, I already said, and I am a research scientist at RIKEN in Wakoshi at Saitama Prefecture, same prefecture as you. So my research is around nuclear physics and astrophysics, and today I will introduce this subject here to you. But first, let me tell you what I think is the aim of today's seminar. It's not only about physics, but I think it's a bit of cultural exchange between Japan and my countries. So I have two countries. I will explain later why I have two countries. Common language, it's English, because I cannot speak yet Japanese. So now I'm learning Japanese. I cannot speak Japanese. So please try English. If you cannot, maybe you can ask him and translate. Then after, I will tell you about my scientific career in science. And later, at the end of the talk, I will tell you about astrophysics and nuclear physics. So these two pictures here. And I will show you the link between astrophysics and nuclear physics. So it's completely two different scales. It's very small and very big. And I will try to make a bridge here. So my countries. So this is a map of part of the world. Japan is here. And my countries are Algeria, which is here, and France. Maybe you know more France than you know Algeria. So I am not half, which means my mother and my father are both Algerian, but they went to France to study when they were young. And then I was born in France. If you are born in France, then you get French citizenship. So I have two passports. I have Algerian passport because my parents are Algerian, and I have French passport because I was born in France. So I spent 10 years in France and 17 years in Algeria. So after their study, my parents went back to Algeria, and they grew up there, and then went back again to France. But I will tell you later what it is. So let's start with France. So I don't know what you know about France, but I'm sure all of you know this. Or, you know, this is Eiffel Tower. And in Japan you have something bigger, a sky tree. And let me tell you the difference. This is Eiffel Tower, this is sky tree, right? It's 2 times bigger than France, huh? Than Eiffel Tower. So then, in France, we eat strange things. So we eat cheese, we eat frogs, but we don't eat frogs, we eat only the legs. But I never ate. I'm not brave enough to eat this. But I eat snails, and it's really good. It's really good, you should try. But I love cheese. This is very, very, the more the cheese is smelly, and the better it is. And I think it's like natto in Japan. Who cannot eat natto? I can eat natto. So, are you Japanese? You are not Japanese. You should try. Where are you from?
Colombia.
Colombia. You should try. It's really good.
I tried.
You try. You don't like. Okay. It's too bad for you. Then we have also, you know this Mona Lisa? It's in the Paris, and this is very famous museum called Louvre. And the first time I went to Louvre, I want to see Mona Lisa, and I was very disappointed because this is the hole, and it's here. It's very small. I didn't know. I thought it's much bigger. And not only this, but usually it looks like this. So you have to queue around to be able to see the Mona Lisa. So it's very small, and you have to make a long queue. So I was not so happy about this. But okay, there is not only Paris in France. There is also very nice, maybe this is you know, it's called the Entretat. It's in Normandy, and it's in the north west of France. It's very nice, but it's usually very cold. I prefer the south. You know Côte d'Azur? It's Mediterranean. This is near Cannes, where there is the film festival every year. Cannes is somewhere around there. This is called Nice, not Nice. Nice. This is very, very nice city. I really like it. And so this is maybe enough for France. So I want to talk now about Algeria, my second country. And I am from a city called Constantine, which is just in the northeast of Algeria. And we call it City of Bridges. And I show you the picture of Constantine. And it looks like this. So it's really a rocky city. So all the city is built on some big rocks. And you have to connect the cities with bridges. So this here bridge, we have also roadway there. And it's very nice. If you look here below, it's really nice. But you should not jump without return. There is also a very nice bridge that I took only once in 17 years. I took only once because it's really scary. It's only for pedestrian, no cars. It's very small and narrow. When you walk, it's a bit moving. If there is a wind, it's really scary. But many people take it and there is no problem. So you should not worry about that. So it's really nice city. I really like it. So now you see here, Algeria. There is a lot along coast. I want to show you the coast of Algeria. It's really nice. So this is one of the most famous hotel on the coast, and it's really nice view with it's like paradise, and it's really nice coast. But we have also mountains, so we have ski resorts, very nice landscape. But what I showed you now, it's if you look to Google Map, this is just here. So in Algeria, 99% of population, because this is Algeria, it's really big country, but 99% of population lives in 10% of the country. 1% lives in the desert. So my city is around here. But actually, the desert is really nice. It's a very touristic place. It's called Sahara. So this desert, it's not only in Algeria, but it's also in Libya, Nigeria, Mali, Mauritania. It's really big desert. It's called the Sahara. And in Algeria, we had different kind of desert. It's not only one type. So you have dunes, you have also rock desert, but you have also cities. There are some cities in Algerian desert, and they are really nice. This is a very famous city, which all the city is red, because the soil is rich of iron. So iron gives red color. And there are something, these people, they are called the Tuareg. They don't belong to Algeria. They don't belong to Libya. They don't belong to anything, any country. They are nomads. So they don't want to live in a city. So they want to be there by themselves. They have their own, they manage their own lives. We cannot, if there is something happening between them, we cannot, the Algerian government cannot participate. They have to solve their problem by themselves. So they are really unique people, and they live only in the desert. They don't want to settle in cities. So now I want to show you, this is typical Algerian family around the table. And this is a typical Japanese family around the table. It looks very different, right? But if you have good eyes, there is something similar between the two. Can you tell me if someone can find it? What's similar? You can start. You can say it in Japanese. Yes?
Next one, they thinking of the chair was
Yes.
but right one, this.
Very good point. Very good point. You are very close. One other try? Yes?
Don't use shoe.
Exactly. No shoes. Exactly. No shoes in the house. This is exactly what I wanted to hear. Very nice. So in Japan, shoes are not allowed in the house. In Algeria also, not allowed in the house. Because? I don't know. Okay, now I show you typical European family. I don't know if you can see it, but they have shoes. So, first time I saw that, I saw European people go in the house with the shoes. I was shocked. How can they go inside the house with shoes? But then I tried to understand. Because I came to Japan, I also find that people don't go in a house with shoes. And then I tried to make a theory. Why? In both cultures here, which is completely different. And here, this is quite, it's also different, but it's quite close from geography. So I think my theory is maybe because of the height of the table. This is what you said. In Japan and in Algeria, we are quite close to the ground where we eat. It's quite close to the ground. And also you sleep on tatami, so you sleep on the floor. We also usually, this is not so typical Algerian, but I could not find a typical Algerian, but usually, this is usually lower. So we also sleep near the ground. So maybe this is the reason why in both cultures we cannot enter, because we are too close to, we eat close to the ground, and we sleep close to the ground. So then I understood my mistake. I thought, okay, here, they eat high and they sleep high, so they don't need to take off the shoes in the house. So I made a mistake. So I said, maybe if we try to learn from our differences, rather than say, this way it's better than this is not true, this is just different. So maybe the world will be a better place if we understand from our try to understand why people do things differently from you. There's always a reason. So we should always understand this and not say we are better or you are better. So this is my main message here. So now I want to tell you about my career in science, but first I want to tell you something, my dream. So when I was a child, I wanted to be ballet dancer. So when I was and I completely failed, of course, but I want to be a ballet dancer. So at 7 years old, I went to school for preparation. So I was training to enter the school for dancing. But next year, was a war in Algeria. Maybe you didn't heard of it. But, it starts from the 90s, I'm a bit old, and it ends in 2000. And my age at this time was between 8 and 18. So during the war, all arts and sport activity are stopped. So we cannot practice anything. So my dream was cancelled because of this. Then at this time, future was a bit, in my generation, all people my age, future was a big question mark. What we do with our lives. We are in a war, we don't know if we will survive or not, but you know, when you are a child, you keep dreaming. So the only thing I could do is sitting in my garden. This is not really me, but similar, and dreaming about the stars and the moon. I knew there is something there, so I want to study. I thought that there is some answer in I didn't know what, but I wanted to study this. So I kept going to school. So I went to high school called Fadila Sedan in Constantine in Algeria, and graduated from there. And then I went to the university. So this is a quite famous university in Algeria, because it was designed by Oscar Niemeyer, Colombian, I think, South African famous designer. I studied physics there, but in Constantine you don't have astrophysics, and I wanted to learn about stars, so I need to go somewhere to realize my dream. So since I had French citizenship, it was easy to go to France, but the transition was not so smooth. But anyhow, I managed, and I got my. I went to Orsay University. It's called Paris 11. This is near Paris. So I got my bachelor degree, master degree, and PhD degree there. And now I want to tell you what I did for my bachelor degree. So for my bachelor degree, I was studying dust that is in our solar system. So usually this dust that around between Mars and Jupiter, it's always coming to Earth, everywhere, every day, all the time. But it's cleaner in the South Pole. So my supervisor was going, maybe it's his one. He went there to the South Pole, and he collect ice, and I had to clean it and do the undergraduate work. So I had to clean it and find this very small dust in it. So this is what I did in my bachelor degree. Then in my master degree, I studied about neutron stars. So I will tell you later about the neutron stars. Then I went to Geneva to do my PhD. I don't know if you know CERN. This is a big facility in Europe. And I was doing my PhD on nuclear physics. Then I came to Japan. So at Riken also, 2 years ago, no, 4 years ago, to work on nuclear masses for nucleosynthesis study. So today I will tell you about this. And then before coming here again, coming back again, I went to Germany. It's a very nice city. This is the most beautiful city in Germany. It's called Heidelberg. It's the only city in Germany which kept the old buildings and the old German culture. And then I worked at the Max Planck Institute for Nuclear Physics. There is a really good institute there. So I was building ion trap, but this today I will not tell you about this. Then today I am a research scientist at Riken. And now I study origin of chemical elements in the new universe. And today I will tell you about this. But first, let me show you something. Do you know this? Do you know? So maybe you are too young to know, to know this. This is please. Star Trek, yeah, exactly. Enterprise, yes, this is a US Enterprise from Star Trek. So you don't know this because you are too young. But the old generation knows about this. And the mission of Enterprise is explore strange new worlds, blah, 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 to boldly go where no man has gone before. So today, I think I am inside this ship. So I realized my dream, or just start realizing my dream. So now I can go into the ship and go to the universe and study the stars. So I want to tell you something here, not just to show you. I want to tell you, find your own dream, not your parents or teachers, your own dreams. And please, never give up. You should never give up. You should keep working to realize your own dream. Maybe one day you can go to your own ship and go to the place that you want to go. Please, do your best. So, now we switch to the physics. So today I will tell you how these chemical elements were produced. You know all this. You know all this table? No, you don't know. Okay, so this is called the periodic table, and these are all the chemical elements that are important for life. For example, oxygen. There's also calcium, iron, for example, carbon, And all life on Earth needs many of these chemicals. But we don't know how these elements are made. This is the question I want to answer today with you, or try to answer, or try to give you direction where to go. But most important question is this. So, why iron or why gold is more expensive? Do you know? So, today I want to answer this question, but I can give you a hint. So, iron is here, and gold is here. So what's the difference? What's the most important difference? It's okay, different elements, but what's more important? Anyone? Okay. Yes, please.
ゴールド、リがアトミックナンバー。
Exactly. Yes. Yes. Bravo. Gold, it's heavier than iron. Please keep this in mind, because the rest I will emphasize why this. Okay. The answer is in the stars, specifically in the life and death of stars. So this I will show you today. But first, before I tell you about the life and the death of a star, let's locate ourselves in the space and also in time. So, where are we? Do you know? Okay, I give you a hint. What's this? Do you know what's this? It's a galaxy. What's the name of our galaxy? Japanese people should know this. All of them. Because you have yes.
In Japanese?
In Japanese? What is it? In English, it's called the Milky Way. It's a translation, huh? Milky Way. And actually, you can see the Milky Way, right? From Earth. You can see, if you are lucky and not in a big city, you can see this is the Milky Way. And what I want to show you here is the universe is not freeze, it's moving. But we don't see the stars moving, of course, because every night they are almost at the same place. But in 3.75 billion years, this, what you see here, small here, this is Andromeda. It's another galaxy. It's the closest galaxy to the Milky Way. And it's approaching. It's coming. They will collide. our galaxy and Andromeda will collide. And then in 3.75 billion years, the star will look like this. This is you can find in a NASA, this Andromeda colliding with our galaxy. So maybe in 3.75 billion years, they can meet. They have to wait a bit more. So this is what I would say. So now we locate ourselves in the space. Now I want to locate you in this time. What is time? So we are here. The beginning of the universe is called the Big Bang. This is time 0. And now we are 15,000 million years after the Big Bang. So, do you know the Big Bang? All of you? Okay, so you heard about it. But the Big Bang, at the end, all the universe was in very small point, which is here. All the universe, what you see, all of you were all in this point. And then it started to expand. So this is time scale, and this is temperature. Start to expand and cool down. So this you can see expanding and cooling down, expanding and cooling down. And what I want to tell you today, I don't want to talk about this because I cannot now, so I will just speak about this 2 periods. After between 300,000 years and 1,000 million years ago. Or after the Big Bang, sorry. So this period was where the first atoms start to build up. So this is what I want to talk to you about today. And we are here, or not? Okay, so let's come back to our question, why the gold is more expensive than iron. Okay, I can answer immediately this question. I have to show you, I have to explain just this. So, this is called abundance of chemical element. Abundance means how much of, for example, if we take this, oxygen is there in the universe. So the chemical abundance, the abundance chemical elements, the graph looks more or less the same in the whole universe, in our solar system or in any other star. It looks quite similar. So here, this is the abundance in a logarithmic scale. And this is the atomic number. So this is heavier and heavier and heavier isotopes. So iron is here, and gold is here. So if you look here, 95 to 99% of the universe is helium or hydrogen. The rest is all what you see here, because this is logarithmic scale. No? So you see here, iron, there is here, this 6. Gold is nearly 0, which means iron is 6 order of magnitude more than gold, which means on Earth, 1 ton of iron equivalent, you can find only 1 gram of gold. For me, this is why it's expensive. It's rare, because it's rare. Also because it's prettier and whatever other reason. But you see here this curve here. This curve here depends only or strongly on nuclear property of these isotopes. what's nuclear focus? For example, let me show you first what's nucleus. So if you take some piece of wood and zoom in micrometer, 10 to the minus 6 meter, you can see already some atoms. Then if you zoom, take one atom here and zoom in, you can see electrons around, and this is nucleus. So today we are interested in this object. It's called nucleus. And if you zoom in again to femtometer, 10 to the minus 15 meter, then you will see it's not just a ball, but it's addition of two nucleon, we call this nucleon, protons and neutrons. But I will not talk about this today, so we stop here on this. So, now I want to explain what's nuclear energy or nuclear binding energy. So if you take, for example, helium. Helium is 2 protons and 2 neutrons. What's the mass of the helium? We would say it's the number of protons times the mass of the proton plus the neutron number times the proton, the mass of the neutron. So just addition those. But actually, this is not true. It's very strange. So if you measure the mass of the helium, you will find it lighter than the mass of all constituents. What happens? Maybe you all know this. So this means energy equal mass. So what happens in the nucleus is the nucleus, part of its mass, it's converted to energy. And this energy is used to hold all particles together. This is what we call binding energy. This is what makes the nucleus a nucleus, which hold together. Because otherwise, if there is proton and protons, it's too charged, they tend to go from each other. So you need to make everyone together. And this energy is using their masses and converted to energy to bind them together. So this is exactly the same energy that we use in the fission for nuclear power plant, or unfortunately in nuclear bomb. And also, today we will talk more about this fusion, which is the energy of stars, and what is now we will talk about. So let's come back to the abundance curve. So to explain how all this happens, first we need to divide this to 2 parts. So first I will tell you how light elements were produced. Then I will tell you about a family of gold, or all heavier elements, or where they So it's not easy to explain, but I try to make it as simple as possible. So this is, first I want to tell you where. It can happen in really giant stars. So this is what you see here, it's red giant. To give you scale, it's 1.6 billion kilometers large. If this is Jupiter orbit around the sun, it's as big as this. But these stars had a really small, it's mainly helium, and hydrogen, as you know, 99% of the elements. But at the very small core here, there is something happening. And this something is, first, there is a fusion of burning, what we call it, helium or hydrogen burning. And then you have some nuclear reactions happening in the star here, in the star. So first you have helium and carbon together, and then oxygen and helium together, and making heavier and heavier nuclei. And then other nuclear reactions. Here we are in the scale of stars, but nuclear reactions happens in there. We have to keep this in mind. So other fusion reactions, and then we end up with iron. So all of this is a series of, and it's accumulating in like from the lighter one to the iron core. So to give you now the idea of the time scale, so to convert hydrogen to helium, you need 7 to 6 years. To convert helium to carbon, you need a little bit less. To oxygen to silicon is 6 months. And from silicon to iron, you need only 1 day. But then, after this, we call it core collapse, this giant star collapse, and then explode. And this is what we call supernova. This is exactly what's happening in this world. So this is how lighter elements are born. And now I want to speak about this. This is much more complex. But first, let me tell you where. In supernova. So after the collapsing or explosion of what I showed you before. So supernova explosion looks like this. It's very, very beautiful. But it's very dramatic change. And to give you an idea about, so this is what the supernova looks like before it explodes, or the star that makes the supernova. And our star, the sun, it's type G. So it's very small compared to this. And to give you an idea about the sun and the size of the Earth, it's really, 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 really big. It's really a huge explosion. Then, other place is neutron star. Do you know what's a neutron star? Neutron star is like solar mass compressed in 10 kilometers. So I don't know if you could imagine this. I cannot imagine this, but imagine this huge, we are here. So 10 kilometers, you cannot even see. All this, it's compressed in 10 kilometers. This is extremely, extremely dense object. So it's because of this compression, it's only soup of neutrons. And a little bit of, at the crust here, there are some other elements. But it's mainly neutrons, like a soup of neutrons. And what do I want to say? Yeah, it's really, it's like a quantum object, but 10 kilometers big. You cannot imagine how big it is. But what is more important here, what I want to say, is the production of heavy elements can occur in neutron star merger. Merger means when two stars merge together. Let me show you a small video here. This is neutron star, and this is another neutron star, and they are, when they come together, because it's very dense, they have very gravitational field. So they start to rotate, 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 until they merge together, you can see. And exactly at the moment when they merge, this makes maybe 1 second. Maybe all elements that you see here, this are produced. This is scale of few seconds. All elements that you know here exist, they are produced only in a few seconds. So this is extremely fascinating process for me. There is also other extreme thing. It's called the binary system. So you have very small neutron star and giant ray. So the two objects that I showed you before. And because this neutron star is very compact, it has really huge gravitational field, which sucks the matter from the big one. So this wins. And at this, when this happens, when all the matter is getting on this small object, you have some X-rays beams that you have some burst, we call burst. And then, at this moment, few seconds, these all elements are produced again, or some of the heavy elements are produced. So, now I showed you where. Now I will try to explain how. But to explain you how, I need to show you what does it mean in isotopes. Maybe there are many chemists here. Do you know what's an isotope? Yes.
The number will be
Exactly. Perfect. Right. Right answer. So then you don't have to explain yourself everything. Then for oxygen, for example, you have 3 isotopes. Oxygen, if we go here, maybe you don't see it very well, but here it's written 8. This is number of protons. So for all this, the number of protons is the same, which means 8. And but number of neutrons is different. So this is definition of isotopes. Now, the question is, oxygen have more than 3 isotopes. Maybe the chemist will be shocked, but this is true. Oxygen have 1, 2, 3, 4, 12. Maybe this one doesn't count. 12 isotopes. But these isotopes, they live very short time. For example, this one, the longest one, no, this one, lives 122 seconds. More extreme one, this one, lives 8 milliseconds. So there are many isotopes, but they don't exist on Earth. What exists on Earth is only stable. We call stable isotopes, which lives forever. But there are others, and because there are others, these are produced in the stars. And now I try to explain how from this we get to the stable ones. So now if I show you everything, so for oxygen we have 10, for nitrogen we have more, carbon, boron, beryllium, so so the difference between when you go up, this is proton number increasing. So nitrogen have 7 protons, right? And oxygen have 8. So here we are increasing the number of protons. Okay? So there are many, many unstable isotopes. This is what we call nuclear chart of rare isotopes. We call them rare isotopes. So if you plot here, it's exactly the same what I showed you here. So it just I showed you for all elements. So if you plot the neutrons and protons, and this is increasing neutrons, and this is increasing like this, increasing protons, you will end up with a nuclear chart. And what I plot here is half-lives. We call half-lives, so how long they live, these isotopes. Well, the black ones that you see here, there are very few. These are stable isotopes that you can find on Earth. But the others, all the others, they are produced in stars or in laboratory. This is what we do actually. I will explain later how we produce this. Okay, so now you know this now. This is again, I plotted the nuclear charge, protons increasing, neutron increasing. So here I make some, showed you the iron is here, uranium is here, gold is somewhere here, I think. And now I try to explain how these elements are produced, the stable ones, the black ones, how are produced in the stars. So in this really, really explosive supernova, or in this star merger, or any other extreme condition in the universe, you have in some of these sites, you have something called air process. Air process means rapid neutron capture. So what happens here, for example, if you have neutron star, which is only neutrons, you have a lot of neutrons around you. So if there is iron, for example, somewhere, and there is a lot of neutron around him, he will capture some neutrons. And he will become heavier and heavier. So for example, if, let's say not iron, but nitrogen, start to capture neutrons and goes in this direction. So this is we call neutron capture. But at some point, you cannot continue like this because of some nuclear property of this nuclei. They start to decay. This is called beta decay. Beta decay means neutron is transformed into proton plus electrons. What does it mean if neutron is converted to proton? How are we going? So we are going neutron minus one neutron plus one proton. Which direction we are going? We are going like this, right? So I capture. For example, I stop here, and the beta decay starts. What happens? Okay, let's say here. So beta decay to this one, and then there is another beta decay, and then I go to the stable. So I produce fluorine 19. So this is neutron capture, beta decay. Neutron capture, beta decay. And this is exactly what happened in the stars. So you capture up to some point, and then you decay. And when you have a stable doesn't decay, so it stays there. And then you have it. We produce the element that are on Earth. So this is what I showed here. So neutron capture, decay, neutron capture, decay, neutron capture, decay. And then you end up with solar, or the abundance that I showed you before. Maybe you don't remember, but it looks quite the same. Huh? So here, for example, hydrogen is here, the iron is here, the peak, and there's another peak here around 50, another peak here about 80. So it's exactly the abundance of element. So this is called the error process. But now you will ask me, how is this error process? So this error process path will determine how much of which isotopes get more than the others. And this path here, it's mainly determined by the nuclear property of nuclear far from stability, or the rare isotopes. So this is what I told you before, that I showed you this, and I told you this is mainly determined by nuclear property. So one of the most important nuclear property for this error process is the mass. So you remember this I showed you? I will give you maybe homework for this, so please remember this. So we want to measure this binding energy, or measure the masses, but we want to measure masses not here, because these are still easy to measure, and we know them, and we want to know the ones that are far from stability. We want to measure the masses of isotopes, or rare isotopes, that lives only for a few minutes, or a few seconds, or a few milliseconds. Huh? So we want to know these masses. So this is what we do at RECON. But first, before we measure the mass, we need to produce them, because they don't exist on Earth. Huh? So we need to produce them. And we have a facility at RECON called RIBF. And you can find information about this in this link. But actually, you can find a very nice movie on YouTube. You can type RI Beam Factory. RI Beam Factory. So you can type this on YouTube, and you can find explanation how they produce rare isotopes. Is it okay? Now? Okay, now we need to measure these masses. So for this, we use something called storage ring. So our storage ring in RECON looks like this. So it's really big. It's basically a ring. And we have isotopes. I don't know which direction is it. I think the isotopes coming from here, right? And then we store them here, and they turn. And we measure their energy. But let me explain how is the principle of the storage ring. It's like a track. So you have isotopes running. So this is a heavy isotope that we want to measure. And this is another one, but lighter. So we want to measure both. So what we do, we inject them in the ring, and we let them run. Who will be faster? Maybe light one. So we just measure the time. Say, go ahead, run, and we measure the time, and from the time we can deduce the mass of these. If they are faster, they are lighter. If they are slower, they are heavier. But in reality, it doesn't really look like what I showed you, but it looks more like this. So we inject them. They start somewhere here all together. And then we let them run in the ring. And then where they are running, they start to separate. Because these ones, for example, are heavier than these ones. And then when they arrive again to what we call time of flight detector, this means time of flight means how much time they fly, because they are flying, they are not running. No? So we call it time of flight detector. So when they arrive here, this one arrives first, and then it arrives this one. And then we can deduce the mass. Of course, it's not as simple as this, but this is somehow the big idea. So, of course, if you are interested, you can join our team. It's called the Isospin Laboratory at the Nishina Center. So this is part of our team. It's not all the team. So I am here, and these two people are French. It's a very international team. There's a lot of Japanese, of course, German, the Ukrainian, German, Hungarian, Chinese, and she's Fumi Suzaki-san. She's from Saitama University. She's his student. And she's working on storage ring. And there are 3 people here, I see, that are working at the storage ring. Please raise your hand. There's 2 on the back that are working with us, and they both work at the storage ring. So please, if you want to come and visit, you can talk to them. They will tell you how much fun it is. I think, of course, you can also find information on the Nishina Center website. If you are interested, this is our team leader, Tomio Saka-san, but you can find more information here. And then, I don't know if I can give them more. Can I? Okay, so it's very easy. Yeah? It's not so difficult. You will not have any grade, but it's fun to calculate. So what I wanted to do is to calculate the binding energy per nucleon in MEV. MEV means mega electron volts for 2 isotopes. Now you know what's the isotopes. Carbon-12 and carbon-14. So first calculate this. You will need this formula. And obviously you will need the mass of the carbon-12 in atomic mass unit. Mass of carbon-14 also in atomic mass units. Mass of proton in atomic mass units. And mass of neutron in atomic mass units. And of course you need definition of atomic mass unit. The unit of the mass unit is MeV per speed of light square. So when you make this calculation, please, I will help you here. Please look to this formula here. Look at this formula. This is mass in mass units. This is also mass in mass units. This is also mass in mass units, and this is energy. Please be careful here. I want you to give me the energy not per mass units but per MeV. So to make a conservation of this unit, so it should be units, the same unit everywhere. So you have to divide this. The mass is equal energy over c squared. So you have to use the Einstein formula. Okay? So please be careful when you calculate the binding energy. It's it's not. I want you to give me by MEP, but you have to be careful with this. And also, per nucleon, what does it mean? I don't want the total energy. I want energy that each nuclear wants to have. So we have to divide by the number of all nucleon. Nucleon means proton plus neutron, all of them. So you have to make sure that the binding energy that you calculate is per nucleon and not the total binding energy. You have to divide this over the total number. Also, when you calculate this, it's fun to calculate, but I want you to understand something here. I want you to tell me which one is more stable. Does anyone knows what's the link between the binding energy per nucleon and the stability? What does it mean if one nucleus has more binding energy than others? This is stronger. He can keep all his nucleons together. So you can, I gave you some answer indirect. You have to calculate binding energy per nucleon and then find which one has the biggest binding energy. Yes. You don't have to do it now, but try. Homework. If they want, can take a note. It's not like that. No, if there are any questions.
Can I take a picture?
I should have printed it, but I didn't have that.
Now we can move to the question time.
Yes.
宿題ですから、今やらない。ちょっと今飲み物持ってきますんで、ちょっと盛り上げとってください。クエスチョンタイム、クエスチョンタイム。
何か質問ありませんか？何でもいいですけど。
Why I go at weekend? This is the question. Why I go to weekend? Very good question. Okay. Today, in the world, weekend is the only place where extremely rare isotopes can be produced. Let me show you. You can find this here, but I can mention it. So in the world, everywhere, there is no facility that can go somewhere here. Maybe there are some other facility who can do some of this here. But weekend is the only place where very, very rare isotope can be produced. So this is why I am here, because I want to study all these isotopes And RICAN is the only facility, or RIBF is the only facility in the world that can do this. And you can find more information in this. Yes.
Why do you choose Japan to research?
Okay, I have to tell everyone. First, because there is RICAN. So in RICAN is the best facility in the world. So in Japan Japan is now the leading country for nuclear physics. Also, I want to go to some place where I don't know the culture and I don't know the language. I want to learn more, not only physics, but also culture. So maybe don't be afraid to go to other countries, because you can learn more, not only physics, but maybe other things like shoes problem or other interesting things. For me now, I am like a child. Everything is new. This is it's really great to be a child.
What Japanese culture is most surprised?
This is very difficult. Everything.
For example.
For example, in trains, I was very surprised. It's very quiet. In Europe, you cannot sleep. Impossible. With us. Also in the street, very clean.
Do you want to drink Japanese tea?
Yes.
Tea in Algeria?
Yes.
Which is more popular, tea or?
It's green. Depends. In the south, people drink
Tea.
because it's very warm. If you drink tea, it's better than water. You can keep more water.
But in the part of the Algeria, you have custom to drink coffee.
Coffee, but also in summer we drink tea, and usually in winter time we drink
So you don't drink hot tea.
hot tea, only hot tea. This also was surprising for me. Cold tea. I never drink coffee.
はい、質問。
Sorry,
はい。
may I ask about the homework?
Yes.
What is this NNZE?
Sorry.
Sorry, I don't know.
Okay.
Nothing. I know nothing about it.
Set.
Yeah, then
Number of protons. How many protons? And H is number of neutrons. So, for example, carbon 12. How many protons? 6. And neutron is 6. So, Z 8.
thank you.
So they equal Z plus. And this is total number of neutrons.
出てくる。じゃあダメだ。シュレッダーかけだとダメだよ。それは個人的に。ごめん。ありがとう。
はい、じゃあ皆さん一つずつ質問を言わないと返さない。じゃあ、この辺から質問できますか。結構しないとあれだって言ってたよ、鈴木さん。足来ませんでした。はい。山口さん、ちょっと質問。いいですか。
はい。
What is the most interesting experiments have you studied?
Nuclear physics.
Physics.
Most interesting.
Most interesting. Have you studied?
Okay. I have two favorites. So first one is this one because it's really pretty different from what I did before. But other one is experiments at CERN. It's doing mass measurements with the traps. So instead of having it was at CERN. This is what you mean? You mean experiments, the setup, or experience of life or physics or work? Okay. During my PhD work, it was at CERN at Geneva. This is in Switzerland, and there we were doing. I find it very extremely beautiful experience because you trap a very small object in what we call ion trap, and you try to see how it moves inside. And then you measure the mass from the frequency of this movement of this small trap. And in reality, it looks like this. It's very small. It's also very small. But it's really nice experience in Geneva. I recommend to go to do some measurement of traps. That's also a star brain because, as you know, This trap is very, they can measure the mass, but it's very slow because you trap it, right? It's not moving, but it's decaying because it's dying. Because it's rare isotopes. They live only for a few, very short time. In traps, it's quite limited. You can do very rare isotopes, but at some point you start to be limited. And then you need storage ring, because storage ring, you can really trap very fast. They can run very, very fast, milliseconds even. This is why they are my true favorite.
Okay.
You said after the Big Bang,
Yes.
the universe was cooled down.
Yes.
So why they could cool down?
I wish I could answer this question.
クールダウンする理由
Do you know why?
I'm sorry, thank you.
I think because it's expanding.
Yes.
It's expanding. So if you have small objects, it's very hot, and then when you make it bigger, then it starts.
さっきのったんでさ、あとはテンペレチャー、デンシティをテンペレチャーをさせてないじゃない。
Exactly, yeah. So maybe you can explain
Thank
that.
you very much.
考えちゃう。みんな取るのが最初。
The space is expanding, and is it continuous forever?
This is very, very, let's say, hot topic in the cosmology now. We don't know. We don't know.
It's not clear.
It's not clear.
Yeah, okay.
There is a possibility that it will expand forever. There is another possibility that it just stop and stay. And there is a possibility that it will shrink back. There are three possibilities. They don't know yet. So it's a research topic by its own, this expansion of the universe.
People come to Japan, did you have any friend or where you come?
I have no
So
words.
how could you work?
Because I don't have friends. I didn't understand.
So how
How I did okay. Okay, so there is a program called GSPS, Japanese Society for Promotion of Science. So you can apply to this, and you get a fellowship, and then you get some money, then you can come and work at Japan. It's very good for going to. I think there are similar programs in Europe or in the US. So if someone is interested to travel, they can apply in this kind of.
Constantine University have a faculty of science,
Yes.
department of physics,
Yeah, there's department of physics, but
biology, chemistry. All departments are included in the Constantine University.
at my time was there was everything. It was physics, biology, what else? Literature, all literature like languages, human science or whatever, resources, many other subjects. But now the university is getting bigger and bigger. So now they split it to 3 universities. So there is university which is specialized in biology, other in law and whatever, and literature. And it's separate. It's not only one university, but now
It's okay.
Is there any obstacle while researching because you're a lady?
This is a very good question. I hear a lot about women having trouble in research, but I never felt this. But maybe where I worked, it was always a good condition. But at least at Recam, I don't feel any difference between me and male partners. So there is, of course, maybe women has to do sometimes more efforts to make people listen to you. Sometimes you have to show that you are stronger, even same level as a male. Maybe you listen more to the male than to the woman, but you have to be strong.
Okay.
And say, never think about yourself as a woman. Just think about yourself as a human being, and think about yourself as you want the other to understand what your idea. Always think this is the most important, that you want them to understand, or you want to understand something. And I think everything would be fine if you believe in yourself.
Okay, I'll be with it. Thank you.
はい、じゃあ次の質問。
はい。
What kind subject do you like?
In physics.
Physics. Describe
His question is, what kind of subject do you like? For example, physics, biology, chemistry, or history, paint, language, something.
Ah, okay, of course I like physics because I'm doing physics. So always do what you like to do. But also I'm very interested in languages. I like very much languages. But since I also start to work on this chemical elements, I start to get interested in chemistry and life science, because then everything is related somehow. Huh? So there are some connection everywhere. Everywhere you can make connections. So like for me, I study the stars, but from the nuclear point of view. Someone can study the stars from the chemistry point of view. Someone can from the cosmology, from particle physics. You can approach it from different way, but this is my main interest, is what's happening in the universe and why we are here and why the chemical elements are.
Thank you.
はい、じゃあラストクエスチョン。いいよ。
I live in Waco.
Ah, really?
Do you know this character?
Ah, yes, I like. What's his name again? Wakochi.
And Satsuki-chan.
Satsuki-chan. I didn't know about Satsuki-chan. I didn't know this one. I know this one. This is his sister. Okay. Thank you for letting me know.
可愛いよ。見てって。
はい、じゃあラストクエスチョン。
マジ。
Do you make experiments in your home?
Experiments in my head.
Or your room? Or by yourself? Like not even...
it's not like chemistry where you can mix things. But
for example, your own I don't know, telescope, for example.
This I don't have.
Just
It's expensive.
programming, anything on the internet, like for your own entertainment. Do you make something by yourself, only for yourself?
I would like to have an electronic lab to make electronics lab in my place, but my house is very small, so I don't have enough space. But I plan to make electronics lab at my place. But for the moment, I don't have it.